Hello, I want to explain the Monty Hall problem using Python. And I'm going to assume that you've heard of Monty Hall problem before. This is so famous, so if you haven't, you should look up articles or videos on this one. Okay, so I'm going to explain my code first and then run it. Uh, so there's the contestant who has a choice to change to the other door that the host didn't choose or to stay. So there are two variables to keep track of which would be the correct or which would be the better answer. So the correct by staying, I put a 0 first, correct by changing, I put a 0, and this will be the counters to keep counting how many we got correct by staying and how many we got correct by changing. First, the contestant will make a guess between the doors 1 to 3, right? And the prize will also be behind doors 1 to 3. And of course, there are 3 doors. Now, in the next 4 lines, I am trying to think about how the host will choose the doors. So the host, of course, cannot choose the door that the contestant chose. So I removed the contestant's guess from 1, 2, 3. So I removed the number from here. And also, if the prize is in a different door, that one's another door that the host cannot choose. So if not guess is equal to prize, then I'm removing the prize door as well. So that leaves the host with either one or two possibilities, and he'll, if there are two, he will randomly choose one of them, okay? And then now we're going to count which strategy will be getting you the prize, okay? So if the contestant's guess is equal to the prize, then of course it will be correct by staying. But if it's different, then that contestant should have changed, and because if the prize and the guess are different, then the host chose the other one, so it leaves you with just one more door, and therefore the contestant will get it correct just by changing to the other choice. Okay, so that's what's going to happen. And then after running this 10,000 times, I'm going to print how many would have gotten correct by staying and how many would be correct by changing. So let's try to run this. And as you can see, there's about 2/3 probability of getting correct by changing rather than staying. So this is counterintuitive, right? But what's really important here is, I put in bold here, is that the contestant, not the contestant, the host is assumed to know what's behind the doors. Okay? And you could remove this condition and try to run the same simulation, and the result will be very different. So it goes like this. The host who doesn't know what's behind the doors will just pick another door, and then if it reveals the car, then automatically the contestant loses, so the host says, sorry, you lost. Okay, that could happen, right? So there's no strategy to be done in that case. But if by chance the host reveals the one with the goat, then the host will be will be able to give the contestant a choice to change to the other one. So that is in the second code. And if you see, this is what happens. The host chooses whatever the contestant's guess is not. So out of the doors 1, 2, 3, I remove the contestant's guess, and the host chooses anything that the contestant didn't choose. Okay. Now, if the guess is equal to prize, then it would still be correct by staying. But if the host choice is equal to the prize, then it will reveal the car, and there won't be any chance for the contestant to make the change, right? So this wouldn't be accounted for. So this is the case when you can't say it's correct by staying nor correct by changing. So it doesn't work. Okay. But if the host choice was wrong and the contestant's choice was wrong, then it will be the case when the contestant would have gotten the prize by changing. So you have this case. And then if you print this result, you see this time they're about the same. So you see that in Monty Hall Problem, what's really important is this assumption that the host knows what's behind the doors, and he deliberately chooses the one that does not have the prize, the car behind. And this kind of makes sense because the moment that the host reveals the door without the prize, there's some kind of information that the host knew that's transferred to everybody. Everyone knows that the host knew that that door did not have the prize behind them. Okay, so in you know how in Bayesian probability, probability is viewed as a way to encode knowledge. So the information that the host had is now let out in the open to everybody by this process. And where did that information go? Well, that information actually changed the probability. That's why this is so important. So I hope these codes will get you to think why the Monty Hall problem works and why in Monty Hall the most crucial part is this sentence right here.